Dear students, so today let us we study about nuclear reactions and nuclear fission. As you know, the nuclear reactions are those in which changes occur in the nuclei of atoms, resulting in the formation of new element or an isotope of the same element. I repeat, the reaction in which changes occur in the nuclei of atoms, resulting in the formation of a new element or an isotope of the same element, is called nuclear reaction. This nuclear reaction is also called nuclear transmutation. There are two types of nuclear reactions. One is natural radioactive decay and second one is nuclear bombardment reaction. Natural radioactive decay we come across in the heavy elements whose atomic number is greater than 92. The nuclear bombardment reactions, they occur both in heavy elements as well as in lighter elements also. In all nuclear reactions, both atomic number and mass number are conserved. In a nuclear equation, both charge and mass are to be balanced. Atoms of mass number greater than 200 decay spontaneously by emitting alpha, beta or gamma rays. Subsequently, a stable nuclei is formed. Thus, nuclei lying outside the belt of stability form daughter nuclei falling in the stability zone. The first nuclear transmutation was demonstrated by Rutherford in 1919 when he bombarded a sample of nitrogen with alpha particles. So here I have given the equation: nitrogen atomic number 7, mass number 14. When it is bombarded with a helium nuclei, that is nothing but alpha particle. So Rutherford got oxygen 817, it is an isotope of oxygen, plus a proton, hydrogen 1, 1. Here alpha particle is called a projectile and the emitted proton is called ejected particle. Now coming to the types of nuclear reactions. Based on the type of the projectile and ejected particle, nuclear reactions are of following types. Of course, there are many nuclear reactions are there. So as far as the syllabus is concerned, we have 6 types of nuclear reactions you are going to study. The first one is alpha N reactions. When I say alpha N reaction, alpha particle is the projectile and a neutron is the ejected particle. So the example for this is magnesium 1224 plus alpha particle gives silicon 1427 and neutron 01. In all these nuclear reactions, the atomic number should balance, as well as mass number also should balance, both in reactant and product side. In the first case, you have atomic number 12 for magnesium and helium 2. 12 plus 2 is 14. So we have in the product side, the silicon atomic number is 14 and ejected neutron is not having any atomic number. Now similarly, the mass number. So the magnesium 24 plus helium 4, 24 plus 4, 28. Out of 28, the silicon is having the mass number 27 and neutron is having the mass number 1. 27 plus 1, 28. This should be used for all the nuclear reactions. The second example for this is beryllium-49. When alpha particle is bombarded to this, we get carbon 612 giving out neutron. Similarly, boron 510 plus alpha particle gives nitrogen 713, which is an isotope of nitrogen. Lithium 37 gives, when it is bombarded with alpha particle, gives boron 510 giving a neutron. Coming to the second type of a nuclear reaction known as alpha P reactions. So the example for alpha P reactions, so I have given here the fluorine 919 when it is heated by the alpha particle gives neon 1022 plus hydrogen 11. So similarly, nitrogen 714 gives oxygen 817, boron 510 gives carbon 13 isotope, magnesium 1224 gives aluminium 1327. In all these cases, the proton is ejected. Now, in these reactions, what exactly you have to remember, I have given the various examples, so that we shall study what would be the new element that is going to be formed. So what is the relation with that, with the earlier element, that we take in the next slide. Coming to the P alpha reactions. In P alpha reactions, proton is a projectile and alpha particle is the ejected particle. Example, lithium 37, when it is bombarded by the proton, we get the 2 helium atoms. That is, the 2 alpha particles resulted. Fluorine 919, when it is bombarded with a proton, we get oxygen 816 and giving out alpha particle. Similarly, the nitrogen 714, when it is bombarded by the proton, gives carbon 611 and the proton helium, that is alpha particle. The remaining other 3 types which you have to remember are PN reactions, NP reactions and N-alpha reactions. Here also the various examples we have given. So in case of PN reaction, proton is a projectile and neutron is an ejected particle. The oxygen 818, when it is bombarded by a proton, gives rise to fluorine 918 giving out the neutron. Similarly, the sodium 1123 gives magnesium 1223 and a proton, and a neutron. Boron, when it is bombarded by a proton, gives rise to carbon 11 and a neutron. Nickel, when it is bombarded by a proton, giving rise to copper and a neutron. Similarly, coming to the NP reactions. In case of NP reactions, neutron is a projectile and a proton that is formed is an ejected particle. The nitrogen 714 gives rise to carbon 614. Magnesium 1224 gives rise to sodium 1124. Silicon 1423 when it is bombarded by a neutron giving rise to aluminium 1323 and a proton. Similarly, you have the fluorine 919 gives rise to oxygen 819. Lastly, we take N-alpha reactions. In case of N-alpha reactions, neutron is a projectile and alpha particles are the ejected particles. The lithium 36 gives rise to the tritium and alpha particle. Boron 510 when it hits to the neutron giving rise to lithium 37 and alpha particle. Aluminium 1327 when it is bombarded with a neutron gives rise to sodium 1124 and the alpha particle. So the students, you have to remember all these types of the reactions and the examples. In this slide, I have given in general, suppose if the projectile, the emitted particle is alpha, what would be a new element that is going to be formed? So this I have given in these slides. Now coming to the first one called the alpha decay. So in case of alpha decay, so the ejected particle is the alpha particle. If you take an element X whose atomic number is Z and mass number is A, then the resulting, the new element, that is X dash, its atomic number becomes Z minus 2 and mass number becomes A minus 4 and gives an alpha particle. So the diagram also I have shown here. Coming to the beta decay. In case of beta decay, so the ejected particle is a beta particle or nothing but it is an electron. So when electron is ejected, if an element X with atomic number Z and mass number A, the new element that is formed will be having atomic number Z plus 1, but its mass number remains the same. So during the emission of beta particles. Here I have given all the previous some of the examples in generalized statements. Sometimes such questions also will be asked. Now coming to the third one, suppose if a positron is emitted during the reaction, then what would be the new element formed? So the new element formed will be having the atomic number Z minus 1 and mass number remains the same as that of a nuclei which is used during this nuclear reaction. Now coming to the electron capture. Electron ejected is beta decay. Electron capture is beta particle is added to the nucleus. Suppose if I take a nucleus of X with Z atomic number and A mass number, the new element, that is X dash, will be having Z minus 1 atomic number and mass number A remains the same, and it emits X-rays. X-rays are nothing but They are electromagnetic radiations. Coming to the another one, the gamma emissions. During gamma emissions, the atom of atomic number Z and mass number A remains the same, and a electromagnetic radiation of very high frequency is given out, and this is what we call it as in this reaction it is called relaxation. Coming to the lastly, the spontaneous fission. In spontaneous fission, the neutrons are ejected. So let us we take an element X. So its mass number will be A plus B plus C, and its atomic number will be Z plus Y. During nuclear fission, it results new element X dash, whose atomic number becomes Z and mass number becomes A, and there is another element X double dash, whose atomic number becomes Y and mass number becomes B, and results the C number of neutrons, whose atomic number is 0 and mass number is 1. Even in these things I have shown with a diagrammatic way also. By this table, the students, you might have understood the nuclear reactions much better also. Here in this slide I have shown the nature of these particles. Alpha particles, it contains 2 protons and 2 neutrons. Beta particles are nothing but it is a electron, negatively charged. Positron is nothing but positron, positively charged, but the mass of it will be the same as that of the electron. So proton is having positive charge. So neutron is neutral. Gamma radiations are very high energy electromagnetic radiations. Now coming to sometimes they may ask, what is the difference between chemical reactions and nuclear reactions? You have studied the chemical reactions are those where the electrons of an atom are responsible. In nuclear reactions, nucleus of an atom is responsible. In chemical reactions, it forms the new compounds. The different elements they combine and forms new compounds. Here in nuclear reactions, the new element is formed. This is what I have given in this. The first one, the chemical reactions involve some loss, gain or overlap of outer orbital electrons of the reactant atoms. In case of nuclear reactions, they involve emission of alpha, beta and gamma particles from the nucleus. A chemical reaction is balanced in terms of mass only. Nuclear reaction is balanced in terms of both mass and energy. The energy changes in chemical reactions is very much less when compared with nuclear reactions. The energy changes are far more than the chemical reactions. In chemical reactions, the energy is expressed in terms of kilojoules per mole. In a nuclear reactions, the energy involved is expressed in MeV. MeV means million electron volts per individual nucleus. In chemical reactions, no new element is produced since nucleus is unaffected. In case of nuclear reactions, new element or isotope may be produced. This is what the difference between chemical reactions and nuclear reactions. Now coming to the another aspect known as nuclear fission. In 1939, Otto Hahn and Fritz Strassmann discovered nuclear fission. So what they did, when the nucleus of uranium-235 is bombarded with slow neutrons or thermal neutrons, it breaks up into two nearly equal parts with the liberation of some neutrons and a large amount of energy. They used uranium-235 when it is bombarded with a thermal neutron or a slow moving neutron. So we get the krypton 3694 and barium 56139 giving 3 neutrons. And also this type, there are some other, the fission will be formed. Sometimes uranium-235 breaks into xenon and strontium giving 4 neutrons. In some of the cases, it may give even rubidium and cesium giving 2 neutrons. Among all the three, the first one is generally a predominant one. Thus, the fission of uranium-235 occurs in about 35 ways. During this process, as many as about 90 isotopes have been produced. The unstable fragments undergo radioactive decay till a stable isotope is formed. The process of splitting up of heavy nuclei into two roughly equal fragments with the liberation of few neutrons and a large amount of energy is called nuclear fission. The nuclear energy liberates in the form of heat. During fission, one atom of uranium-235 produces 211.5 million electron volts. 1 kg of uranium-235 releases 8.68 into 10 raised to 10 kilojoules of energy, which is a very huge number, huge amount, which is equal to burning of million liter of petrol or energy released in the explosion of 20,000 tons of TNT. TNT means trinitrotoluene. The neutrons released during nuclear fission causes other nuclei to undergo fission, thus sets in the nuclear chain reaction. This chain reaction of nuclear fission is the basis of nuclear power and nuclear weapons. In a nuclear reactors, nuclear energy is produced by controlling the chain reaction. This energy is used for the production of electricity. In atom bombs, by sudden uncontrolling the nuclear chain reaction, large quantity of nuclear energy is produced, which is used for the destructive purpose. Now let us study how exactly the nuclear fission takes place. Various theories have been proposed for this, and one of the theory is known as liquid drop model of nuclear fission. Bohr and Wheeler explained the phenomenon of nuclear fission on the basis of liquid drop model. When a thermal neutron hits to uranium-235 nucleus, the nucleus oscillates, sets inside the nucleus. This deforms the nucleus into elongated shape and then into narrowing ellipsoid shape. The energy released due to chain reactions turns ellipsoid shape into dumbbell shape. At this stage, Coulombic repulsions of the two positive parts becomes predominant, which results the compound nucleus into two major fragments with the emission of neutrons and high nuclear energy in the form of heat. The huge amount of energy released during fission is due to mass defect. It has been calculated that the energy released during fission of one atom of uranium-235 is 211.5 million electron volts. I have shown the diagram where a neutron is bombarded to the heavy nuclei. So this neutron enters into the system and there is a oscillations starts in the nucleus that leads to the elongation and which further leads to the ellipsoid shape and then into the dumbbell shape and finally divide into two, giving the neutrons as well as the energy. The diagrammatically I have shown here. These are the diagrams of the same in a different fashion. So here also have shown the same thing. The liquid drop model of nuclear fission, how the liquid drop model takes place. Now coming to some of the reactions, the nuclear fission reactions. As I have told you, the second one, uranium-92-235, when it is bombarded with a thermal neutron means slow neutron, its speed is less. And it turns into the uranium-92-236, which is unstable. It turns into the 85% of it turns into the barium 56-141 and krypton 36-92, giving 3 neutrons. These neutrons are fast neutrons. They have high energy. And during this process, 202.5 million electron volts per atom of uranium-235 is generated. Similarly, we can also produce the nuclear fission by uranium-92-233. This is synthetically produced, that is artificially this isotope is produced from the thorium 90-232. So when from the thorium we get uranium-233. This also when the thermal neutron hits into this nucleus, so we get strontium and xenon and 3 fast neutrons, and energy evolved is 197.9 million electron volt per atom. which is comparatively lesser than the uranium-235. Coming to the third one, that is plutonium-239, which is also the artificially or synthetically produced from uranium-238, which exists in large quantity. When uranium-238 is bombarded with a neutron, so we get plutonium-239. So this plutonium-239 is further, when it is bombarded by a thermal neutron, so we get the plutonium-240. 73% of it turns into zirconium and xenon. Zirconium-103 and xenon-135. During this reaction also, the 3 neutrons are produced and energy evolved is 207.1 million electron volts per atom. So, these are the 3 important nuclear fission reactions. If these reactions are controlled and energy produced is used for the peaceful purposes, that is the production of electricity. If this energy is uncontrolled, then that principle is used in the preparation of atom bombs. Dear students, go through these things and try to learn. Thank you.